guest today, so let me get to the floor here. On the floor, Dr. Deanna Hooper. Hi, Deanna. So wonderful to have you here again. How are you?
Yeah, hi, Christian. Hello to everyone who's joined. It's really nice to be back with the iTelescope network. I joined last year twice, and I'm really happy to kick off the talks of this year as well. I'm really looking forward to telling you all about cool stuff in the early universe today. So it's really, really nice to be back here.
So we're going to way back, way back past Hannibal now, right to the beginning of time somewhere, right? Is that what it's going to be about today? It's very exciting. We've never done that here.
Yeah, we're going to go back as far as we possibly can today. I'm going to spend most of today talking about a very small amount of history of the universe, but it's going to take me quite a while to get through it. So yeah, we're going back as far back as we can today.
Off you go. We're looking forward to it. Thank you, Deanna.
Sure. We have two polls we wanted to run at the beginning, right?
Okay, right. Let me just do that here. Okay, 1 second. So you want me to run that right now? I will do that. Okay, here we go. We launched this one. Let me just do that. So it's even got a picture on, as you can see. That's new. Okay, so the question is, can you just read it out, please, Deanna?
Yeah, so we have kicking off with a question of what do you think the Big Bang is? We've made this a multiple choice question, and the 4 answers you can choose from are the origin of the universe, a big explosion, the earliest time we can talk about, and a singularity like a black hole. And the reason we're running this poll is because there's a bit of a misunderstanding about what the Big Bang actually is. I'm pretty sure that most of you will get this question wrong, which is why we're running it. And then throughout the talk, I'm going to convince you as to what the correct answer to this question is.
Okay, so don't hold back. It's multiple choice. You can take several answers, right? That's unusual, right? Okay, well, we'll get another few seconds going.
Yeah, I see someone in the chat is just talking about Steven Weinberg's book called The First 3 Minutes, and that is excellent because I'm going to make that exact reference once we get started as well.
Very good. That's exciting. I think Steven Weinberg died recently, didn't he? I think
a few years back. Yes, yes.
Back. Yeah, that's right.
An amazing mind, did a lot of really nice things for physics.
Yeah. Okay, I will end the poll and I'll share the results now.
Let's see. Okay, so 43% of you think it was the origin of the universe, 11% a big explosion, nice. 59% say the earliest time we can talk about, love that. And 30% say a singularity like a black hole, excellent. I love that we have quite a broad range of answers here. So I can already tell you it is definitely not a big explosion. And then we're going to see between the other 3 which is the correct answer.
Oh.
Maybe we can run the second one now as well, because it will be really interesting to see what you think about this one.
Yes, give me 1 second. I'm just trying to find it because they've changed things again here.
Yeah, Zoom updates make everything complicated.
1 second. Give me a second. Where are we? Here we are. Yes. Okay, here we go. Okay, so what is the earliest time in the universe we have been able to study? That's the question. Yes. Okay.
Yeah, and this is deliberately ambiguous because you might argue, what do we mean by study in this case?
Yes.
So it is purposefully ambiguous here, and you can only select one. So what is the earliest time in the universe we have been able to study? Your options go as early as 3 seconds after the Big Bang and as late as 500 million years after the Big Bang.
So I can tell you I already got it wrong, okay? Because I was thinking of Deanna, and instead of thinking scientifically, I thought psychologically, right? I thought, which picture, what's her favorite picture? And then I came to a certain conclusion, which is not the answer, actually. So.
Which is not the correct answer. So anyone who knows me well, don't go with what you think I would put as the answer. Okay, I'll share that now. I'll wait a few questions on. So hurry up, please. I'm going to close it in a moment. So just it's okay if you get this one wrong. Just pick one.
Yeah,
pick whatever you think sounds right.
Okay, I'm going to share the results. There you go.
Nice, nice. Okay, so a few of you selected 3 seconds. Not many have selected 3 minutes. And we have 300,000 years. A lot of you. I expected.
That was me. That was me.
Yeah, I expected a lot of you to select 300,000 years, and that is incorrect. Okay, lovely. We will come back to this later. I'm not going to give the correct answer now, but I will, close to the end of my talk, we're going to revisit this question. Okay, so now I can jump straight into the talk. Let me just bring up my screen. Okay, so yeah, today we're going to be talking about, I have the slightly amusing title of What Goes Bump in the Early Universe, obviously playing on the thing of what goes bump in the night. So I'm going to be talking about all of the stuff that goes bump in the early universe. We already had the comment here in the chat about Steven Weinberg's book called The First 3 Minutes. And that is exactly what we're doing today. We are going to talk about the first 3 minutes of the universe. So we're going really far back in time. And I'm going to spend about an hour telling you about 3 minutes. So before we jump into that, I just want to say, like, what does the universe look like today? What's our current starting point? And if we look around in the cosmos, there are 3 main components. Everything you see, everything you're accustomed to, everything from the sky, the stars you see in the night sky, to me, to my coffee mug, all of this is normal matter. And normal matter only accounts for 4.9% of the energy budget of the observable universe. There's another 26.2% that is in the form of dark matter. So dark matter is this weird type of matter that interacts via the gravitational force, but it doesn't interact via the electromagnetic force. This means that we can't actually see dark matter in any way. Dark matter and light do not really interact. Light just passes through dark matter. And calling it dark matter is not really a correct name. We should actually call it invisible matter. It would be more correct. But it's quite hard to study dark matter because it is invisible. But then there's another 68.9% of the universe, which is in the form of dark energy. Dark energy is driving the accelerated expansion of the universe, and that's pretty much everything we know about it. And I'm not going to talk about dark matter and dark energy too much today. I already did a talk for the iTelescope network all about dark matter and dark energy, so I'm not going to talk about that today. But what I want to talk about is, how did we get here? How did we go from an early universe to this? So this is the ingredients, and now I want to draw up the recipe of how you build the universe, how you build what we see in the night sky today. So we have to ask the question of, how did we get here? And I'm starting with this sketch of the evolution of the universe. This is the sketch that a lot of people draw up. You might have seen different versions of this. On the one hand, on the left-hand side, on the far left, you see the Big Bang, and on the right-hand side, you see today, 13.82 billion years later. We know, to the best of our knowledge, that the universe is 13.82 billion years old. And you can see the very first thing you have on the left here is the Big Bang, which, if you're taking this, would mean Big Bang is the origin of everything. And I'm going to argue in 2 minutes that that is not true, that this is an approximation we do, and actually with the Big Bang label in this plot is wrong. But I'm going to come to that. So there's a lot that's happened in the universe. We've gone through a murky stage initially. At some point, we had particles appear. At some point, light broke away. Then galaxies formed, stars came on, galaxies formed, and eventually we came into the picture. And there's a lot one could talk about here, but I'm really just going to focus on this tiny part at the beginning. So this is everything I need to set the scene as to what the universe looks like today. So the ingredients of the universe today were fixed in these first 3 minutes. So we're going to talk about the first 3 minutes. And technically, it's like the first 100 seconds. But at some point, Steven Weinberg called it the first 3 minutes. I'm sticking to that theme. So today, we're going to talk about the first 3 minutes. And I'm going to start with a disclaimer. We are going so far back in time that a lot of what I say is going to be hypothetical. A lot of it is going to be speculative. And there's going to be a lot we do not know. So I'm going to be very careful to say things of like, this is what we know, this is what we're unsure about. So I'm going to raise a lot of questions here that don't have answers. And unfortunately, we're not going to get answers to all of the questions that I'm asking today, because this is really far back in time. But later on, I will convince you that we actually know a lot more than you might think. So we're going to jump into this very early time. And do put your questions in the Q&A. I will stop twice during the talk to take a couple of questions, and then we'll go through most of them at the end. But from past experience, we don't get through all of them, so get your questions in quickly in the Q&A, because we normally get quite a few of them here. So going back to the first 3 minutes, I'm going to start the same way Star Wars starts, in a long time ago in a galaxy far, far away. Except in my case, I'm talking about a long, long time ago in our own universe. And this is what we're going to do, a long time ago in our own universe. So if we look out at the night sky today, if we look out at the cosmos, we know that the universe is very, very, very big and very, very, very cold. There's a lot of stuff in the universe, but it's very far apart and everything is overall very cold. However, we also know the universe is expanding. So if we take this back, that means in the past, the universe must have been smaller. You've rewinded enough, and at some point, the universe must have been a lot hotter than it is now, a lot denser than it is now, and a lot smaller. And here I want to put a caveat, because I'm saying it's a lot smaller, but I'm also going to tell you that the universe is infinitely big. So when I say it's a lot smaller, that still means it's infinitely big. It's just a smaller infinitely big than the current infinitely big. And this might sound like a weird mathematical thing, and it is, but the universe is so vast and so ridiculously big that we can't even imagine its size. And even 13.82 billion years ago, this was still true. It was just substantially smaller than it is now, but it was still infinitely big. So infinitely big universe, just a smaller infinitely big. And based on a few things that we've been able to see in the universe, we think that it spent a while growing exponentially. Now, unfortunately, over the last few years, we've all come accustomed to exponential growth and how things propagate exponentially. So, when we're talking about exponential growth, it means it's growing really, really quickly, like doubling in size every day kind of thing. And we believe that the universe spent quite a while growing exponentially. But here's the cool thing. This period of exponential expansion is what we call inflation. And we don't know how long inflation lasted. So this period of exponential growth could have lasted 10 billion years. It could have lasted 1 second. We don't know, because by its own nature, the way that inflation happens, any knowledge that existed beforehand gets erased, it gets deleted, because inflation just pushes everything away from each other so much that there is no way we can figure out if anything came before inflation, and if so, what came before inflation. So inflation is like a reset button in the universe, which means we can't talk about stuff that happened before inflation. With this in mind, when we say the universe is 13.82 billion years old, what we're actually saying is, since inflation, 13.82 billion years have passed, which means the time we start our clocks is actually after inflation, not before inflation. So then if we go back to the question that I asked you all of what is the Big Bang? The Big Bang is this idea that the universe was very hot and dense and smaller than it is now, and grew exponentially and eventually led to the universe we have today. It's the model that we use to describe this. But the event that we describe as the Big Bang is the point where we start time. It's our t = 0. And this is after inflation. So if I go back to this figure here, you see this figure shows Big Bang and then cosmic inflation. But a lot of physicists actually argue that you should flip these two around. You should have cosmic inflation first, because this could have lasted another few billion years, and then the Big Bang. So when I say Big Bang, what we're talking about is the origin, or the earliest point in time we can consider. And this was one of the options in the poll. Some of you put that the Big Bang is the origin of time, and I would agree with this. The Big Bang is the first time we start counting. But the Big Bang is also the earliest time we can consider. Now, there was also the question there of, or the possible answer of, the Big Bang is a singularity, like a black hole, and that is also true. So I said at the beginning, most of you will get this wrong, and the reason for that is because there's actually 3 correct answers out of the 4 I gave you in the poll. So the Big Bang itself, it was not an explosion, but it is the earliest time we can think about. It is the origin of time, because it's when we set our time = 0. And it is a singularity, because a singularity just means it's the point where our equations break down. And the reason I want to make this distinction is because a couple of years ago, people were talking about a model of dark matter where dark matter was produced during inflation. And there was some confusion because the scientists involved said dark matter was created before the Big Bang, meaning this inflationary period that we set before the Big Bang. But of course, because most people think Big Bang origin of everything, anything before the Big Bang makes no sense. So I just wanted to digress slightly on what it means when we say Big Bang. And throughout this talk, you'll see that now I'm not going to refer to things happening after the Big Bang. I'm going to talk about things happening after inflation, because that's actually when our clock starts. The Big Bang itself is just the ambiguous name we give to this thing in the early universe. In any case, we have this period of exponential growth. We're pretty sure that there was this period of exponential growth. So I have the question in the title of my talk of what goes bump. The first thing that went bump was the universe itself. The universe itself grew exponentially. Now, of course, there's the question of why. Why do we think that inflation is a thing? Why do we even need something like inflation? There's two main reasons to think that we had inflation. They are both problems with our standard picture of cosmology. There are two problems that we cannot solve unless we add inflation. Now, the first one is what is known as the flatness problem. Now, when we look out in the universe looks like it's very, 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 very flat. And this is something that might be a bit hard to wrap your head around because the universe is four-dimensional. There are 3 space coordinates, 1 time coordinate, right? You can move up, down, left, right, in, out. This is 3 dimensions. So then how do you visualize a flat surface when we're talking about a 3-dimensional object? And there are several different ways you can think about this. The mathematical way is that if you go anywhere in the universe and you draw a triangle and you add up the angles, you're going to reach 180 degrees. This is a very unsatisfying answer. What you can actually think about is Einstein's general relativity has told us that objects with mass will curve space-time, and the curvature of space-time tells objects how to move. So if space-time is curved, it tells something how to move. So with that, you can go somewhere in the universe, far away from galaxies and from stars, find a cosmic void where there is nothing. And you put an object down, you put a ball or a planet in the space where there is nothing else. In a flat universe, that object is going to stay exactly where you put it. But if there is curvature in the universe, this object is gradually going to move because of the curvature. So when we say that the universe is flat, it means if you remove all the gravitational objects, there is no background curvature left. So you can do this game if you take a planet, you put it somewhere, it doesn't move, that means the universe is flat. But why is the universe flat? Because the number that gives us the curvature of the universe, it's just a number. It could be negative, it could be positive. And a flat universe means that curvature is exactly equal to 0. And of all the possible numbers it could take between minus infinity and plus infinity, why is it 0? And it's very nice that the universe is flat because it makes our equations a lot easier. We get a whole thing in our equation that we can just cross off. So it's nice that the universe is flat, but why is the universe flat? And this is something that is known as the flatness problem. And inflation provides a solution to the flatness problem. Now, if you have a universe that grows exponentially in its infancy, then any curvature is going to be stretched out. And the analogy here we can do is imagine you have a balloon and you have an ant walking on the surface of the balloon. When the balloon is not very inflated, the ant is going to see this is a curved surface. But as you blow up the balloon more and more and more, it's going to stretch to the point that imagine you blow up your balloon to the size of a hot air balloon. The ant walking along your hot air balloon is going to say, this is flat. As far as I can see, there is no curvature. So if you have enough inflation, no matter what curvature you start with, the universe is driven to be flat. So we can say the universe might not have been flat before, but with enough inflation, it's flat today. So this is one reason to believe in inflation. And another one is what is known as the horizon problem. And the horizon problem is very weird, and I've never found a satisfying sketch to explain it, so I've made my own. So let's see if this works. Now, in the universe, you can have pockets that are in contact. And the thing that is in contact with each other is going to reach the same temperature. This is something we're quite used to. If you take food out of the fridge and put it on the bench and you come back a few hours later, the food is going to be at room temperature because it's balanced out. When it's in the fridge, it's not touching the air outside, but when you put it touching the air on your kitchen counter, it's going to balance out the temperatures. If I turn on the heater in my room, it's going to gradually make the whole room the same temperature. but the rooms that are not in contact with the heater are not going to reach the same temperature. So you can imagine we have these different patches of the universe that we're going to call in causal contact. And it's what I'm showing in the left with these dotted lines, these dashed lines. And you see you have one patch where all the particles have a property that I'm going to call green. Now, color is not a realistic one to use. It's just one that lets me make the example. So you might have a patch of the universe that has the property green. You have another patch that has the property yellow, and you have another patch that has the property purple. If the universe just grows normally, today, when you look out in the universe, everything we can see would be this gray circle that I'm calling observable universe. And within the observable universe, you would expect to find green and yellow and purple. You would expect to find a bit of everything. But what we actually find is if you measure the temperature of the background of the universe, whichever direction you look in the night sky, you measure exactly the same temperature with tiny, tiny, tiny differences, but an average temperature of 2.73 degree Kelvin. So that part of the night sky and that part of the night sky and any part of the night sky where you put your thermometer, unless you're putting it in a star, you're going to measure the same temperature. So then the question is basically, why are we not seeing different temperatures? Or in my picture, why are we not seeing different colors when we'd expect there to be green and yellow and purple? Inflation solves this problem. So this is known as the horizon problem. It's basically, why does everything within our horizon look the same when these things weren't in the same horizon in the past? Inflation provides a solution. So I'm going to show the same image now where we have the one on the left and then it grows. But instead of growing normally, I'm now going to make it grow exponentially. So we go from having the same thing on the left to having a substantially bigger universe now. And with this, you can see that everything has grown so much and everything has been pushed so much that our gray observable universe now lives within one circle from before. So now instead of having green and yellow and purple, the yellow and the purple are not even on my screen, they don't fit. And everything within our universe is the green property, or the 2.73 degree Kelvin. So the way that inflation solves the horizon problem is by saying the universe grew so much that everything we see today was inside the same pocket in the past. And it was inside the same pocket that could share the same temperature. And this part that could exchange information grew so much that it's everything we see today. So another observable universe very, very far away might be able to see the yellow or the green or the purple. But our observable universe is small compared to this whole amount of universe that we have because of inflation. So with inflation, we solve the horizon problem. We go from having things that are disconnected to actually only seeing things that were connected, that were neighbors in the early universe. Flatness problem and horizon problem are the motivation for inflation. So, okay, very, very early universe where we haven't even started our clock yet because we don't know how to start our clock. So we're talking about something before t = 0, just because we set t = 0 after the inflation. But this is something that happened in the early universe. We're pretty sure of this because otherwise we can't make sense of some things. This process might have lasted a few billion years. We don't know. So let's start our clocks now. Inflation has happened. What comes next? Well, the first thing that happens is we're going to start forming the first fundamental particles. Now, the very first particles in the universe are going to form. And now is the big question. Why is there something instead of nothing? Where did particles come from? We have no idea. The current idea that we have is that all of the energy that was used to inflate the universe is still lying around. And this energy can then be converted into particles. So the leftover energy from inflation can reheat the universe and produce particles. This is not confirmed. This is just our best guess. Now, at the time when we create particles, we also create antiparticles. So every particle, for an example, an electron, is the particle that moves about inside electricity cables. An electron is going to have an anti-electron, which is called a positron. For every electron, you can have a positron. They look the same, except they have inverted quantum numbers. Basically means they have inverted charge. So if an electron is negative, an anti-electron is going to be positive. The cool thing is that when antimatter and matter meet, it annihilates. If an electron finds a positron, they're going to smash into each other and produce light. So you end up with no particles and just light. But the cool thing is, in the very early universe, we created a lot more particles than antiparticles. For some bizarre reason that we don't understand, there was a bit of an imbalance. For every 1 billion antiparticle created, there was 1,000,000,001 particle, which means every antiparticle is eventually going to find a particle to annihilate with, but there will be a small amount of matter that is going to survive. Why was there more matter than antimatter? We don't know, but if there wasn't, we wouldn't be here to ask ourselves this question today. If matter and antimatter had been created in the same amounts, there would be no matter in the universe, there would just be light, nothing else. So we're only here because there was this slight imbalance, but we have no idea what caused this slight imbalance. So currently, what's in the universe is a particle soup. We've created the first fundamental particles, and there's just basically this plasma everywhere in the universe made up of all of these particles. And we call this the quark-gluon plasma. So I want to talk to you now about what we mean by quark, what we mean by gluon, what are these fundamental particles. So I'm going to briefly show you the standard model of particle physics. These are the 17 building blocks that make up all of the matter in the universe, all of the known matter, the visible matter. Let's ignore dark matter and dark energy. All of the visible matter is made up of these 17 building blocks. And we divide these into 3 families. You can see the purple ones, these ones up here, these first 3. These are what we call quarks. Today, quarks don't exist alone. You always have quarks together. You have quarks inside protons, inside neutrons. Then you have leptons, which are these down here. These 6 leptons can exist alone in the universe. And you see we have things like the electron. So eventually we're going to put these together to form bigger stuff. But for now, this is what we have. And then we have the bosons here in a different color. And the bosons are the ones that tell the other particles how they can talk to each other. And then we have the Higgs boson, and I'll talk to you about that later. The Higgs boson is the one that gives everything else mass. And it's also a particle that we can have. So at this point in the universe, we have all of these particles in a big cosmic soup. You don't have any coming out and creating anything. You just have this plasma, this soup of particles. So a plasma is a place where the electrons are free to move around, and you have like this state that is neither liquid nor gas, kind of this plasma state. So when we're talking about the soup of particles, it's in a similar state. Everything is moving freely around. It's not really bound together in any meaningful way. But I want to talk about these bosons here. I said these bosons tell things how to talk to each other. What they actually do is the bosons carry different forces. So I want to talk about the forces, and I'm going to start by calling on an XKCD. So XKCD is a really fun webcomic. If you don't know it, it's definitely worth checking out. And here's a conversation about the forces, and someone says there are 4 fundamental forces between particles. Gravity, it obeys a specific law, we understand it. Electromagnetism, it also obeys a specific law, plus the Maxwell equations, let's not talk about that. Then we have the strong nuclear force, which holds protons and neutrons together. It's very strong. And we have the weak nuclear force, which every physicist will explain as something about radioactive decay moving on. So then if someone says like, okay, that was a bit weird, I'm going to tell you that there's one of these 4 forces that we don't understand, and you might think that it's the weak force, but actually it's gravity. The other 3 we understand. So if you don't know XKCD, you should absolutely check out their comics. They're really funny. But let's just go a bit more serious here. So how do objects talk to each other? And they talk to each other via the forces. So we have gravity. We don't really know what gravity is, but we know that objects with mass curve space-time. Space-time tells objects how to move. This is a gravitational force. You know, the sun and the Earth are in orbit. The Earth stays around the sun because of gravity. If I drop my pen, it's going to fall down. Gravity. We have a good understanding of gravity until we ask what gravity is, and then our understanding breaks down. Electromagnetism is the second force we have in the universe today. Electricity, lights, magnets, we're familiar with this one. We know how this one works. And we have the strong nuclear force. This glues everything together. And then we have the weak nuclear force, which is responsible for radioactive decay. And again, we trail out off there because it's a very difficult one to explain. So these are the 4 forces we have today. But in the very early universe, when everything was so hot and so dense, and we had really high energies, because when you have more heat in the universe, you have more energy. So we know that the universe is cooling down. That means in the past it was a lot hotter and therefore a lot more energetic. And if you go to high enough energies, these forces might actually blend into one. We know this is true for the electromagnetic force and the weak force. In the past, these were fused together as an electroweak force. So at this point, you only had three forces. You have gravity, you have strong, and you have electroweak, because it's fused together. Now we move into hypothetical. If electromagnetism and weak combine together, why can't the? And there is this idea that if you go to high enough energies, you're gradually going to put the other forces together as well. So if you join electroweak and strong force, you get what is known as a grand unified theory. We haven't figured this one out yet, we're working on it. And then if you want to add gravity to the mix as well, you need a theory of everything or quantum gravity. We haven't figured this out either. So we're not sure how many forces there were in the early universe, somewhere between 1 and 3, but we know for sure that electromagnetism and weak were joined together, and we think the other two might have been as well. So going back to the theme, what goes bump in the early universe? Well, particles go bump because they can use the forces to bump into each other. Let's take a breath. Let's recap where we are, what's happened. We are currently less than 1 picosecond after inflation. This means we're 1 trillionth of a second. If you divide a second into 1 trillion, that's how much we progressed since the end of inflation. We have this quark-gluon plasma. We have forces, we're not sure how many, but we have forces. So what do we currently have in the universe? We have this particle soup. We have some antiparticles, which I've just flipped the soup upside down to depict antiparticles. And we may or may not have dark matter. We're not really sure when dark matter appeared or how dark matter appeared or what it's doing, but we may have dark matter at this point. So we've gone 1 trillionth of a second. I want to take a breath, and I think this is a good chance to take 1 or 2 questions from the audience. I see we have a few in the Q&A. So let's take a breath here, recap, and then we move on and go a bit further forward. So do we have any questions?
Okay, Deanna, thank you so much. I'm going to jump now, just have to sort this out 1 second. There's a person called Israel who wanted to ask something, but the question's incomplete. Anonymous says, how do we know what percentage contains what? Okay.
Love that question. I'm guessing you mean, how do we know, like, this 5% normal matter, yes, 25% dark matter? And I'll show you later how we know, but the answer to this is the cosmic microwave background radiation, which is one of the oldest things, the oldest light we can see in the universe. And it gives us a whole bunch of information. And these numbers, you know, I say 4.9%, we know for sure that it's 4.9%. These are not random numbers. And I'll get to that later, but we mainly know through the cosmic microwave background radiation.
Do you want one more question?
Let's do one more. Okay,
fine. Jean-Pierre is saying, what does a hot early universe mean? No matter, because too hot, then only energy. And what would be the nature of this energy?
Yeah, this is a brilliant question. So when we say hot in the early universe, it means the energy, the background energy is really high. The temperature is really high. Is there matter? Well, we have this quark-gluon plasma by now. So does this count as matter? It doesn't count as energy, but it's not yet in a stage where we can properly call it matter. It's kind of this plasma of particles. You could argue that as soon as we have particles, you have some type of matter, and we have created matter and antimatter by now. What created them? We're not sure, probably leftover energy from inflation, but we do have this type of matter, but it's not in the same way that it is today. It's just in this cosmic soup that we call quark-gluon plasma. So that's the current status. Okay, so let's carry on with the story, and we'll come back to more questions later on. So we're 1 trillionth of a second after the end of inflation, and it's taken me a while to get here. So let's carry on the story. What happens next? Well, some of the matter and antimatter is going to start annihilating. It's going to start smashing together. So some of the particles and some of the antiparticles are going to come together and evaporate, produce radiation. They're going to annihilate. But I'm going to take another step. We just stopped at 1 picosecond, so now let's go to 20 picoseconds. So we are 20 trillionth of a second after the end of inflation. A ridiculously small time. If you want it in different words, it's a fraction of a nanosecond, like 100th or 2/100th of a nanosecond. If the strong and the gravitational forces were united, they've already broken away by now. We don't know if they were or when they separated, but at some point, gravity and strong force have separated. But now, 20 picoseconds after the end of inflation, the electroweak force can break into the two forces known as electromagnetism and weak force. This is something that we're pretty sure happens. So these two forces break up, which means the universe now has four distinct forces. And I'm going to say at this point that the forces are going bump because they're breaking up and doing funky things. I'm going to keep on with the theme of going bump. But something else really cool happens at this point, and this is that the Higgs boson turns on. So I mentioned before that the Higgs boson is something that gives everything else mass. Now, beforehand, the Higgs boson is just kind of lurking there, waiting. But the universe is too hot, it doesn't like that much heat, so it's just waiting. But once we reach this stage where the forces separate, the Higgs boson can turn on. And it's not completely clear if the Higgs boson turning on causes the forces to separate or the other way around. But what happens when the Higgs boson turns on is that suddenly all of these particles acquire mass. And the way to think about this, imagine we had our nice quark gluon plasma that I've referred to as a particle soup. So imagine if you have soup that is very watery and you want to make it thicker. So you might add cornstarch, or in the case of the photo here, you might turn it into treacle. So instead of water, you have kind of this thick treacle maple type thing, maple syrup type thing. So what the Higgs boson does is it adds this resistance to the universe, so that when particles travel through it, instead of feeling like they're traveling through water, they feel this Higgs field, which is like walking through treacle. It's a lot harder. And this resistance of moving through the Higgs field is what we call particle mass. So using the food analogy, we go from having this very liquid soup to having a very starchy, thick soup. And this is because the Higgs boson turned on. So we go from a very a very not dense thing to something that I'm using density or treacle here. It's really not, it's the Higgs field, but it's an analogy as if you were trying to walk through treacle. You meet this resistance, and this resistance is what we interpret as mass. But here's the cool thing. When these forces separate, they trigger what is known as a phase transition. And there's different ways that this can happen. If these forces and the Higgs boson turning on, mainly the Higgs boson turning on, if the Higgs boson turns on everywhere smoothly, then not much is going to happen. It's just smoothly going to turn on. It's like you add cornstarch to your soup and it just gradually gets thicker. But there's another way that this could have turned on, and we're not completely sure how this happens. But if instead of being a smooth transition, it's patchy, you're going to get patches of the universe where you have this new property, which is the Higgs field turning on, and you're going to have patches that don't have this new property. But the new property is the better one for the universe because it's more energetically efficient. It just means it uses less energy. So it's gradually going to expand to become the dominant one. And this is something that can maybe produce gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. And I'm going to show you a video to show you what I'm talking about here. And the video I'm about to show you is an actual simulation done by people in my group. And it's a video of what this bubble patchy evolution of the Higgs boson might have looked like in the early universe. So you see, first we have black, we have the old state. And then gradually we're going to form bubbles of the new state. You see here you have the first bubble. So inside this bubble, you have the new state. And you can see these bubbles are gradually going to expand and take over the existing state of the universe. Of course, when you're not just going to produce one bubble of the new phase, but multiple, and these are gradually going to expand and expand. So this video is an actual physics simulation made by David Weir and my group. You can see that the inside of the bubbles is expanding. When these bubbles collide, they would produce gravitational waves. And this whole turbulent effect that you're seeing here would produce gravitational waves. But you see, if you let the bubbles grow enough, they are going to take over the whole universe. So this is a simulation of what might have happened when you turned on the Higgs boson. It might be a smooth process everywhere, or it might be a bubbly process. And if it's bubbly, you get these really cool simulations and you might produce gravitational waves. And the reason I'm emphasizing this is because I'll come back later to gravitational waves, and I'll tell you that if this produces gravitational waves, we might be able to measure these gravitational waves. It's moving on, moving on. What happens next? Well, as the universe cools down, the strong force actually becomes stronger. And this plasma can change. So instead of having this quark and gluon plasma, these things can actually start clumping together. So your soup is about to get very clumpy. And what can form is 3 quark systems or 2 quark systems. So I told you earlier when I showed you the standard model of particle physics that usually quarks are not found alone. Usually they're bound together. So once you have this quark gluon plasma soup, it cools down enough that it can start becoming clumpy. And what comes out of this is protons and neutrons and what we call mesons. So if you group 3 quarks together, you end up with baryons. If you group 2 of them together, you end up with mesons. And you can see here I have the example of like this patch up here, where you have an up quark, you have 2 down quarks, and you have a bunch of gluons surrounding them. This thing here would be a neutron. If you have this guy here, you have 2 ups, 1 down, and a bath of gluons, and this here would be a proton. So from your quark gluon plasma soup, you can start making actual bigger particles. You can start making protons and neutrons and mesons. Mesons decay quite quickly, they're less stable, but the baryons, these are the ones that still exist today. Now, the reason this happens is because you really have these quark gluons in the soup, but any proton or any neutron is a composite of 3 quarks and a sea of gluons around them. So here the universe is cooling down, the strong force becomes strong enough that rather than leaving everything in a soup, it can start pulling things together. So you form protons, you form neutrons. So particles go bump, but in a quite different way to the way they were going bump beforehand. And I just want to mention that this very nice witchy soup doodle that I have here was done by a very good friend of mine, Sania Hiva. She's also responsible for the Cup of Cosmology logo and banner and does amazing doodle, amazing art. And I requested this specifically for the talk and I'm very happy with it. So from your quark gluon plasma soup, you can start forming protons and neutrons. And the reason this is interesting is because protons and neutrons make up all of the atoms that we see today. So the first seeds are now starting to form actual protons and neutrons. And at this point, antiquarks and quarks are either going to annihilate or be trapped up together. So the antiquarks stop becoming important at this point. So where does that leave us? By now, we are about 10 microseconds after the end of inflation. Whew, you know, I am what, 30 minutes in, 40 minutes into this, and we have progressed less than a second. We are 10 microseconds after the end of inflation. Whew, it's going to take us a while. So what do we have currently? We have protons, we have neutrons, we have other baryons. We still have electrons doing their own thing and anti-electrons. We have neutrinos and anti-neutrinos. We haven't got rid of these antiparticles yet. We have dark matter doing its own thing. We probably have dark energy by now. We're also not really sure when dark energy appeared or what dark energy is doing, but we probably have dark energy at this point as well. More stuff to come. The universe is still cooling down. So now we've reached a stage that we call freezing. Freezing is a really important stage in the universe. And you see I have the slide title here of It's Freezing Outside. This is a play on words because the process that we're going to talk about is known as freeze out. So as the universe cools down, dark matter stops interacting. Dark matter does not like the cold. It's like a bear that goes to hibernate and stops talking to anyone else. This is what dark matter does. As the universe cools down, dark matter stops whatever it was doing. It's like, oh, I'm done. We don't know how much dark matter was talking to the other particles before this point, but whatever it was doing before, it stopped. It's had enough. It's cold. So this means that the amount of dark matter is now fixed. Before, you might have had something like dark matter cannibalizing itself, or dark matter producing more dark matter, or even dark matter bumping into quarks and protons. Whatever it was doing at this point, dark matter says, I've had enough of this, stops doing it, it breaks away. So dark matter freezes out. It's done. Dark matter is now fixed. Around the same time, the weak force becomes gradually weaker as the universe cools down. The weak force becomes weaker, and neutrinos also freeze out. So neutrinos are these particles that travel almost at the speed of light. They're practically massless. They zip through everything. Every second, 60 billion neutrinos are zipping through your thumb. Neutrinos are everywhere. But these neutrinos, most of the ones in the universe, stopped what they were doing at this point as well and just started traveling freely through the universe. So first dark matter, then neutrinos, both say like, okay, we're done, we've had enough of this, it's cold, bye, and they go off and do their own thing. So dark matter has gone away, neutrinos are doing their own thing in the universe. And by now we have reached 1 second since the end of inflation. All of this, we are now 1 second in. And I'm going to say at this point, things stop going bump because dark matter and neutrinos stop bumping into other things. But the universe is still cooling down. As the universe cools down more and more, electrons and anti-electrons can start to find each other. They couldn't before because they were caught up first in the quark gluon plasma, and then there was just too much stuff in the way. But neutrinos have gone away, dark matter's gone away, universe is getting calmer now. So the positrons, which are the anti-electrons, and the electrons can come together. When they smash into each other, they annihilate and they produce 2 photons, 2 particles of light. So you go from having electron-positron to having 2 particles of light, 2 photons. The reason this is very interesting is because this just fills the universe with light. You can't see it yet. The light is still bumping into everything else. The photons are still bumping into everything, except of course the neutrinos and dark matter that have already done their own thing. But this light later on is going to become the cosmic microwave background radiation. But for now, we're just producing this light. We're smashing particles and antiparticles together. They're annihilating and they're filling the universe with photons. What this means is that all of the antimatter from the universe is now gone. You can produce new antimatter after this, but the initial amount of antimatter created at the end of inflation is now gone. So more particles go bump, electrons and positrons go bump, and the photons can now talk to everything else except neutrinos and dark matter, which are doing their own thing. This means that these photons are going to carry information about these events. Okay, so are we done? Are we there yet? Not quite yet. By now, we're about 6 seconds after the end of inflation. I'm speeding up a bit now. We did a long time for the first 20 picoseconds, and now it's like, okay, now we're 6 seconds in, things are getting going. So what do we have? We have baryons, we have protons, we have neutrons, we have electrons, we have a lot of photons, a lot of neutrinos, and we have dark matter doing its own thing, dark energy also doing its own thing. But there's one step that we're missing. We need to go from protons and neutrons to the nuclei of atoms. We're still missing the protons and the neutrons binding together. And this is the next step. And this is what we call Big Bang nucleosynthesis. So as the universe cools down, the protons and the neutrons start talking to each other properly. So if you have one isolated proton, you actually have a hydrogen nuclei, because it's basically a hydrogen atom is 1 proton and an electron. And here we're just talking about the nucleus, so you just need 1 proton. And if you smash protons together, you can fuse them together and produce helium. So there's a whole chain reaction that I'm showing here on the right, where first you get 2 hydrogen that come together. This produces deuterium. So deuterium is like heavy hydrogen. It's hydrogen that has a proton and a neutron. You can see here everything in red in this sketch is a proton. Everything in gray is a neutron. You can also produce some photons, some neutrinos, some anti-electrons. But what you do is you produce this chain reaction, and this is fusion. This is the same thing that happens in stars. You're fusing elements together. In the center of stars, you fuse hydrogen to form helium, you fuse helium to form all the other heavy elements. But the first elements were actually formed here at this point. So we are forming the first nuclei, the first cores of atoms are being formed now. And what we make at this point is deuterium, helium, and lithium. But here's the cool thing. All of the hydrogen and most of the helium that we have in the universe today came from this process. This process here, where first of all, the protons came out of the quark gluon plasma, and then they started speaking to the neutrons. This is where we form all of the hydrogen in the universe and most of the helium. This point here, we're bringing things together. We are forming the first nuclei. They're not yet atoms because they don't have electrons, but they are the atom nuclei. And why is this important? Let's just think about the periodic table of elements, all of the elements that we have in the periodic table. Now, you've probably heard that a lot of elements are formed in stars, and this is true. I'm going to go starting here with like the light blue ones. If you have a white dwarf, which is a tight, really dense star, which is the end of its lifetime, you can see it can form all of these elements here, things like iron and copper. If you have a massive star exploding, a supernova, you can form all of these other things here, like oxygen and sodium and all of these other ones. In yellow and orange, you can also see different types of stars that are exploding and reaching the end of their lifetime. And in pink, you have a nice process of high energy cosmic rays in the universe. But the dark blue ones here, this is Big Bang fusion. And you can see that all of the hydrogen and almost all of the helium are formed in the Big Bang. So all of the hydrogen that we have today in the universe was formed, we say here in the Big Bang, we mean in this event that we call Big Bang nucleosynthesis, this formation in the early universe. So any hydrogen atom that exists today was made here. And the reason this is cool is you might have heard Carl Sagan's phrase of "you are stardust." And this is true, but it's not the full story. So what is the average human made of? Here I'm showing you the average composition of a human. 65% oxygen, we have it up here. Okay, this was formed in an exploding star, stardust. 18% carbon, we have it here, green and yellow. Different types of exploding stars, okay. 3% nitrogen, I'm aware that I skipped one. Nitrogen is here, exploding stars. 4% others. But then we have this 10% that is hydrogen. So 10% of your atoms were made a few minutes after inflation. So when we say we are stardust, that is absolutely true. 90% of you is stardust, but 10% of you is universe dust. Some of my atoms are 13.82 billion years old, and when I'm done with them, they're going to go back to the universe. And this is my favorite fact in cosmology, because nothing makes me feel more connected to the universe than realizing that actually I am literally carrying universe dust within me. This will never cease to amaze me. Okay, so us and our universe dust atoms, let's move on. Where are we now? We have reached the end of the first 3 minutes of the universe. We've gone through a lot. We had inflation, we had forces appearing and breaking, we had particles, we had antiparticles created, they've annihilated. We've produced proton, we've produced nuclei, dark matter's broken away, other stuff has broken away. What do we have now? We have hydrogen and helium nuclei, we have electrons, photons, neutrinos, dark matter and dark energy. We have all of the ingredients. Now you add 13.82 billion years, you wait, and you reach the universe today. At some point, these things are going to come together and form stars. At some point, you're going to form galaxies, you're going to bring everything together. But this is where it started. And I'm not done, because I just told you a lot of stuff. But there's a big question of how do we know all of this? But before we go into that, I'm going to stop and see if we can take 1 or 2 questions, and then we're going to go into why you should believe everything I've just told you.
Very nice, Deanna. Okay, I will go to Agnesisa. I hope I pronounced your name correctly. What ended inflation is the question.
That is an excellent question, and the answer is we have no idea.
Oh, okay.
We don't know what ended inflation or why it ended. There's actually a lot of models or ideas as to what could have led to it to end. There's some of these result in what is known as the multiverse, where you have pockets of inflation that could still be happening somewhere in the universe, and each one of these pockets would have different laws of physics. You can have different mechanisms to end inflation, but the short answer is we have no idea. There are models known as eternal inflation, where inflation is basically still ongoing. We just haven't realized it. So we have no idea what ended inflation, but that is an excellent question. Let's do another one.
Sure. Paul Hess is saying, for each particle, why do we think there were 1 million more particles plus 1 billion antiparticles instead of just the particle we see?
So the main reason is because of the amount of photons that we see in the universe today. These photons needed to have come from somewhere, and the most plausible place they could come from is this annihilation. And also any mechanism you come up with to create matter will also create antimatter. There's no reason why we would only create matter and not antimatter. And usually you produce both. What we don't know is why we produced a bit more. But we know for sure, at least we haven't found a model that can only produce matter. We have to have had antimatter. So both for the amount of photons we can see, and because we haven't found a model that can only do one of the two. And it's great to see you here, Paul. Paul's a regular on my shows. So it's great to see you here,
Yes,
Paul.
that's right. Good.
Okay, So let's save the rest of the questions, because I've just told you a lot of stuff. And a lot of you might be wondering why on earth you should believe what I'm saying when I'm telling you about stuff that happened 13.82 billion years ago. So let's separate fact and fiction. Let's go into how we know all of this. And I'm going to bring back my evolution of the universe picture, but I'm using a slightly different picture now that's just more focused on the early universe. And here you can see we start with Big Bang and inflation. Again, we have this ontological debate as to which came first. We have the universe today, and in between we have a lot of things. This is you can actually get this version as a poster. It's quite a nice one. You can see it tells you, like, here there were quarks, here there were electrons, here we had different things happening. But I'm going to focus on 4 main ways that we can study everything I've said. The first one is going to be light. And you'll notice that this is after the first 3 minutes. This is substantially later, but this is going to be the light that is produced by all of the annihilating particles. The second thing we're going to talk about is the first elements. I talked about the hydrogen and the helium and the lithium and the deuterium that we're producing in Big Bang nucleosynthesis. This is something we can actually measure. Another thing we can use is particle physics experiments, colliders and accelerators that are smashing particles together, trying to reproduce the conditions of the early universe. And then there's my favorite thing that could go all the way across the cosmos, which are gravitational waves. Gravitational waves are ripples in the fabric of space-time. They could be produced at any point in the history of the universe. So it's really the probe that covers everything. And I'm going to go through all of these. And I just want to say I'm very happy to have my gravitational waves oscillating perfectly through the universe. So let's go through all 4 of these. The first one, the cosmic microwave background radiation, one of my favorite things in the universe, apart from gravitational waves. This is the oldest light you can see in the cosmos. It is the background in every direction you look. This is background afterglow of light. They have very different temperature, very, very small different temperature. Right? Most of these photons are 2.73 degree Kelvin, but there are tiny, tiny, tiny temperature differences of the order of 1 part in 100,000. And this is what we're showing here as orange and blue. So this is a snapshot of this background light in the universe. And this was produced 380,000 years after the Big Bang, which is why those of you who know me well and know that I love the CMB, in the poll at the beginning said the oldest thing we can see is the CMB, the cosmic microwave background radiation. This is true. This is the oldest light we can see, but it is not the oldest thing we can see. So when we have these electrons and anti-electrons annihilating in the early universe, it's going to produce a lot of photons. These photons at some point are going to freeze out from the rest of matter, the same way that dark matter did, the same way that neutrinos did. And when these photons freeze out and decouple, they produce the cosmic microwave background radiation. By measuring the cosmic microwave background radiation, we can learn how much matter there is, how much dark matter there is. This is where we get the 4.9% and the 26% and the 69.8%. This is where we get it from. But in addition to all of that, this can tell us about the amount of photons that were produced. So this also carries information about the annihilation of particles in the very early universe. So even though this is something that is 380,000 years after the Big Bang, it tells us information about the early stages. And additionally, it is a prediction in our Big Bang model. And if you have inflation, inflation gives you an explanation as to why there is no preferred pattern in this sky. So a prediction that inflation makes is that when you measure this, you should see an equal amount of spots of equal size. So you won't see a preference for big spots over small spots. Once within the size of the spots that you're looking at, there is no preference, there is no clear pattern. And this is a prediction that inflation makes. So inflation solves the horizon problem on the flatness problem, and for free, it gives us an explanation of why the CMB looks the way it does. So it's a prediction from the Big Bang model. Sorry, it's predicted both by the Big Bang model and it matches predictions made within inflation. Cosmic microwave background radiation, my favorite thing. My 2 favorite things in the universe are this and gravitational waves, and today I get to tell you about both. Second thing I wanted to talk about was measuring the earliest elements. So I mentioned that these elements, this hydrogen, this helium, lithium, deuterium, especially lithium, deuterium, and helium, are produced in Big Bang nucleosynthesis. Now we know that some of these elements are also produced in the inside of stars, But if you can find a galaxy that is really, really young, where stars have not really started to form yet, or galaxies that are really, really distant, where you also have this effect, they're very young galaxies, the further away you look in the night sky, the further back in time you're looking. So if you can find really distant galaxies, they should still have the same initial amounts of these elements. A really good example of this is dwarf galaxies. Dwarf galaxies don't have many stars in them, and you can kind of measure how many stars there are based on everything we know about stellar fusion, how much added element should there be, and then you can calculate, okay, you measure the amount of lithium, the amount of deuterium, the amount of helium in these dwarf galaxies, you subtract the amount you know is being produced by these few stars that you have, and what's left should be what was produced in the early universe. One galaxy that we've used for this is Unanswered 18. As you can see here, it's photographed by the Hubble Space Telescope. It's this nice pretty one down here in the main corner. And you can use this to measure the primordial elements. And you can compare your measurement to the predictions from our model, where we have all of this thing that I've explained. So if what I explained is true, you should measure a specific amount of helium and deuterium and lithium. Helium and deuterium match perfectly. The prediction from everything I've explained and what we observe matches perfectly. Lithium does not. There is 2 times less lithium in the universe than there should be in these primordial galaxies. We have no idea why. This is what is known as the lithium problem. Some people say the problem is that we just haven't understood some of the astrophysics as to how the stars are forming or how it's playing in these galaxies. Other people say this is a problem with our model. But lithium is off by a factor 2 or 4, depending on your analysis. And this has been a problem for over 20 years in cosmology, and we still haven't solved it. Helium matches perfectly. Deuterium matches perfectly. Lithium does not. You might think a factor 2 is not a lot, it's not a factor 10, it's not a factor 100, but it's a factor 2 too many. Okay, we've done light, we've done elements. Let's go on to particle colliders. So I've mentioned throughout that in the early universe, we were at much higher energies, much higher temperatures. This is something we can try to reproduce. If we smash particles together at high enough energies, we can recreate the conditions of the early universe. If you accelerate particles to almost the speed of light and you smash them together, you have a huge amount of energy. In the moment they smash together, you're going to have a huge amount of density, and you're going to have a very high temperature. So you very, very, very briefly reproduce the conditions of the early universe. And this is something they do in particle colliders. For an example, the relativistic heavy ion collider in the Berkeley National Lab, or the Large Hadron Collider in CERN. And this is something that might sound a bit worrying. Why are we playing about with such stupidly high energies? But these are very high energies individually for particles. But in every collision that you do at CERN, there is as much energy in the Large Hadron Collider as in your average lightning bolt. It's a lot of energy if you're a particle. It's not really a lot of energy for us. So it's not something we need to worry about. So you might have heard that the Large Hadron Collider smashes protons together to see where particles are created. And this is a lot of what it does. But what we can also do is try to reproduce the quark-gluon plasma that we had in the very early universe. And to do this, you need a lot of quarks and you need a lot of gluons. So protons are not going to be good enough, because in a proton, you only have 3 quarks, not a lot. But if you use something like gold or even lead, you have over 50 protons and neutrons, which means you're going to have over 150 quarks to play about with. So at the relativistic heavy ion collider, they smash gold particles together. At the Large Hadron Collider, when they're not smashing protons, they can smash lead together. This is what ALICE does. There are 4 detectors at the Large Hadron Collider. CMS and ATLAS are looking for whatever new particles they can find. LHCb is looking for antimatter, but ALICE is looking at collisions of the lead ions, of the lead nuclei. So what happens? I'm going to show you a video produced by CERN down here at the bottom. Red is proton, white is neutron. And you can see you have 2 lead atoms here. So you have a lot of protons, you have a lot of neutrons. And we're going to make these smash together. And this is what they've done at the Large Hadron Collider. And as these come together, you're going to have such a high energy and such a high temperature that for a moment, you can actually rip apart the protons and the neutrons. And you produce this big ball of plasma. But this is rapidly going to turn back into protons and neutrons. This is unstable. You can see now it's already going to start going back into protons in red and neutrons in white, and the plasma in the middle disappears. But let's watch it again, and you'll see for a brief short amount of time, you can actually reproduce quark-gluon plasma. This is something that we have been able to do both at the relativistic heavy ion collider and at the Large Hadron Collider. They have produced this quark-gluon plasma. It's short-lived. It only lasts a fraction of a second. It's enough to say, look, there's a quark-gluon plasma, but not long enough for us to actually study it properly. But what this means is that it shows us that at very, very high energies, you can actually have this quark-gluon plasma. We have been able to see it in colliders. So it's not just a fantasy, it's something that probably actually happens. And then there's a final thing, gravitational waves. So gravitational waves are ripples in the fabric of space-time itself. And I'm not going to talk too much about this because I gave a whole talk about gravitational waves for the iTelescope a year ago. So you can go and watch that one. But briefly, if you imagine space-time, anything that moves within space-time can produce gravitational waves if it's accelerating in a non-symmetrical way. So for an example, if you have two black holes coming together and colliding, this will produce gravitational waves. This is something that we have been able to see here with LIGO and Virgo here on Earth. We have been able to measure gravitational waves coming from black holes smashing together. What a black hole does is it briefly deforms space-time by a very, very small amount. If a gravitational wave goes through you, you will very briefly get taller and thinner and then shorter and fatter. But these gravitational waves are so small that if one went through you, you would grow by a billionth the width of a human hair, which is a ridiculously small amount. So it's not something that is really easy to see, but it can be produced by a lot of things in the universe. And here on the right, you can see kind of a sketch of different things that produce gravitational waves and different types of detectors. And you can see that there are things like neutron stars, and there's also this red thing here, quantum fluctuations. And this is what I want to focus on, the top thing of quantum fluctuations in the early universe. So we know by now that gravitational waves are a thing. LIGO and Virgo have measured them for us. But inflation itself could be such a dramatic effect that it would produce gravitational waves. We expect inflation to produce gravitational waves. There should be a background of gravitational waves in the universe produced by inflation. But also I showed you this cool video of bubbles in the universe. The separation of the electroweak forces into electromagnetism and a weak force. It could have been smooth, in which case you don't get gravitational waves, but it could have been bubbly, like the video that I showed you. And if it's bubbly, it produces gravitational waves. So this would result in a background of gravitational waves. In the same way that we have the background of photons making up the CMB, you could have a background of gravitational waves. But these are substantially smaller than any gravitational wave you can produce by black holes smashing together. Detectors on Earth will never be able to detect them, but one in space might be able to. If we can send a gravitational wave detector up to space, we could potentially measure these gravitational waves produced by inflation and by the electroweak force separating. This is what I'm working on. This is incredibly cool. There is hope to measure this. This is not sci-fi. We are planning a spacecraft. It is going to launch within the next 20 years, and it is going to look for these things. Whew. Okay, so what next? Sorry, no, we have to answer the question from the poll before we move into what next. So I set you the question at the beginning of what is the earliest time we can study, deliberately being ambiguous about study. So how far back can we go? Well, the oldest galaxy we've been able to see up until recently was a galaxy that was produced 500 million years after the end of inflation. That record was beaten very recently by the JWST. The JWST has now found galaxies that are 300 million, that were produced 300 million years after inflation. This is a ridiculously distant and old galaxy. It's amazing that the JWST has been able to see these. So those of you who answered 300 million years after inflation were probably thinking about this, and you are wrong, because we can go further back. The oldest light we can see in the universe is the cosmic microwave background radiation, produced about 300,000 years after inflation, and that's what a lot of you selected as your answer. But that is also not true. We can measure these primordial elements that were produced 3 minutes after inflation. We can measure the amount of helium, the amount of deuterium, the amount of lithium in dwarf galaxies, and we can match this onto what we expect happens 3 minutes after the Big Bang. So the oldest observation we can make is of stuff that was produced 3 minutes after inflation. I said after Big Bang, I am trying to say after inflation, but ambiguous terms there. And we can use this to infer back to the first few seconds after inflation. So if we define study as actually observe, then the correct answer was 3 minutes after inflation, which is the answer that only 12% of you selected. If we go back to actually what we can infer, we go back to 3 seconds after inflation. But I would argue that study means direct observation, in which case the oldest thing that we can observe is the oldest element in the universe, 3 minutes after inflation, so an answer that only 12% of you got. But I didn't expect you to get this right because everyone thinks of the CMB here, but we can actually measure 3 minutes after inflation, which is really cool when you think about it. What next? Where are we? Well, throughout this talk, I said we don't know about a lot of things. We don't know what happened during inflation. We don't know what caused inflation to start, what caused it to stop. We don't know how the first particles were formed. We think maybe it's related to inflation. We don't know why there's more matter than antimatter. We don't know if the 4 forces were united at some point or if only 2 of them were. We don't know how, why, and what dark matter and dark energy were doing in the early universe. We also don't know what's up with lithium. Is it just an anomaly? Does it mean we need to rethink things? What's going on with lithium? Where do we go? How do we answer these questions? Well, there is hope. We have these particle physics experiments trying to produce quark gluon plasma. They're looking further and further back in time. They're going to much higher energies. They are really pushing our understanding of the early universe. We're expecting new colliders, new accelerators in the future to push this even further and maybe get a glimpse of what happened in the first few seconds after inflation. We have ongoing dark matter and dark energy searches. Very excitingly this year, the Euclid space-based mission is going to launch. It's the biggest telescope we have produced to look at dark matter. Within the next 20 years, we're hoping to send LISA to space. It's a space-based mission that is going to look for the ripples in the background of the cosmos produced by inflation, produced potentially by electroweak breaking. This is something we're hoping to do. We might actually be able to look at a gravitational wave that was produced a fraction of a second, picoseconds, after the end of inflation and say, look, I can see directly what happened there. And the cosmic microwave background radiation, the photons there, could also carry imprints from inflation, because inflation would have been so dramatic, it would have affected everything in the universe that came after it as well. And photons could act, the way photons travel through the universe, the direction in which they're spinning, or in which they're vibrating, could actually carry an imprint of inflation. There are some CMB missions that are going to be launched within the next 10 years that are looking for the imprints of inflation in the CMB. So while I didn't provide answers to all the big questions today, we might in the future. So let me bring it all together. I spent about 45 minutes telling you about everything that happened in the first 3 minutes. That we already had the reference to Steven Weinberg's book, The First 3 Minutes. It's an amazing book, it's 300 pages. I managed to do it in 45 minutes, but there was a lot of stuff happening. My question in this talk was, what goes bump in the universe? Well, a lot of things actually went bump in the universe. And even though it might seem like science fiction, it might seem very speculative, we have a surprisingly good idea of everything that happened. But while we know a lot, there is so much more we do not know. But moving into the future, we're going to be able to look further and further back in time. And I think within the next 10 to 20 years, we're going to get some of these answers. Maybe not all of them, but we might get some. And maybe, if we're very lucky, we might find some answers to the biggest questions, like why is there something instead of nothing? So thank you all for listening. There's several different ways you can get in touch with me if you want to. And I think there's several questions we can go to now.